Let us now analyze this amplitude equation that we have derived. So let's write it down first so we have it in front of us. So we have the linear term is modified from the forcing, and then we have the saturation, and then we have the phase sensitive quadratic term in A. And I should make this a curly F. Okay, let's note, I mean, this is a relatively complicated equation because it has 1, 2, 3, 4, 5 complex parameters. F is a dynamical variable the way we derived it, but in fact, for us, it's a control parameter. So it's 5 complex parameters, so that's 10 parameters, that's a lot. So let's do 2 steps. First, we'll focus on the case that we actually have derived. So for that, we need to note down the sign of a couple of these coefficients. So we have that mu2 is actually purely imaginary. How should we write that? Mu2 is equal to mu2r plus mu2i. Let's write it this way. Mu2r is 0 and mu2i is negative. And similarly, gamma I is negative. Actually, gamma r is 0. And it turns out delta is purely imaginary, but let me get back to that later. I should also note that we have mu r is negative and mu I is equal to minus omega. So omega is that detuning, so mu I is that detuning. Okay, so that restricts the cases we're interested in. In addition, note that delta and f are both complex quantities, so they have some argument, meaning e to the I phi, some phase, but we can choose again a star, we can rotate that to actually eliminate these arguments. So let's write now, to simplify the equation, let's write A as some magnitude times a phase, times a time e to the I phase, times e to the I theta. And we'll pick the theta to absorb the argument of delta and f. So let's say if delta was a delta bar times e to the I psi delta, and f was an f bar e to the I psi f, then we can pick theta to absorb both of these angles. So how does that work? As we plug it in, we plug the e to the I theta in here, so we get minus 2 I theta. And then again, from the other side, we get another I theta. So it's 3 I theta with a minus sign, has to be equal to the phase of this thing. So the condition is that we have psi delta plus psi f has to be equal to 3 theta. And so let's pick theta accordingly. And then we can assume without loss of generality that delta is actually a positive number and f is a positive number. So in the following, I'm going to assume that, and I'm going to write, instead of the curly f, I'm going to write a regular f, just because it's easier to write. And that's that. So take f equals f positive and delta also positive. Okay, so now we need to analyze that equation. It turns out to be useful to write it really in magnitude and phase. And so when we do that, we plug that in, what do we get? We get dr by dt plus I d phi by dt times r equals, and so we have on the right-hand side with mu, we have this term mu plus mu2f squared. Now, as I said, f squared is just a control parameter. So this is just a parameter, the whole thing in front here. So let me call this whole thing m. so I don't have to carry around so much. So that means we have actually on the right-hand side, we have m times r, m times r. Then we have minus gamma r cubed, and then plus delta f r squared. Well, not quite. I have to deal with the e to the I phi term. So I have an e to the minus 3I phi, right? Just like before, we get from the left-hand side, we get e to the I phi, and here we get 2 I phi's gives together e to the minus I phi. Okay, so best to split it in real imaginary parts. And again, writing then m is m also in terms of like a real part, an imaginary part, like an mr plus an mi. So I'll write this here as mr plus I mi. And then I can separate in real and imaginary part. I get dr by dt is equal to mr r minus gamma r cubed plus delta f r squared cosine 3 phi. And the imaginary part gives me d phi by dt. And I can cancel an r. Maybe I shouldn't do that yet. Let me keep the r. So I have mi r minus gamma I r cubed plus delta f r squared sine 3 phi. Okay. So we're looking for fixed points. Well, not necessarily fixed points. Let's see. Fixed points would be easy. Is that all we want? Let's think about that. If we find a fixed point, then that means the solution is, of course, then not a fixed point because y is given by a times e to I omega t, right? So that means if it's a fixed point, that just means that it oscillates with a frequency omega naught. And if the phase, this phase here, would tell us whether, if it evolves, would tell us that it oscillates not exactly with that frequency. So if this phase evolves, then the oscillation would be not with the same frequency as the forcing. Or would be not phase locked to the forcing, I should say, because we have, the solution has a 3 omega naught and omega naught in it as frequencies, and but the phi gives the deviation from those frequencies, and so therefore, if phi evolves, we would have not a phase-locked solution. So I'm interested in phase-locked solutions in particular here. So therefore, I'm going to look for fixed points. So fixed points. Phase-locked to the forcing. Meaning the solution is really going exactly at the frequency of the forcing with a fixed phase relationship. Okay. So the one thing that's obvious is that since both equations are proportional to r, there's always a solution r equals 0 for all parameters. So I could call that, it's a fixed point, a steady state, I call it R infinity, and that's the first one, and that's equal to 0. But note, this is not, doesn't mean that y is equal to 0. Remember, y is driven with the forcing as an inhomogeneous term. And you may recall that y1 was actually had a term a times e to I omega naught t. And this a has to do, has magnitude r. So that's 0. but y1 also has an e to the I3 I omega naught t, and that term is still there. So the solution r equals 0 is a solution that oscillates exactly along with the forcing. So therefore y is something like, well, if you look it up, what we had, some factor, but the important part is cosine 3 omega naught plus epsilon squared capital omega times t plus higher order terms. So that's one solution. That's the solution corresponding to r equals 0 or also a equals 0. So let's look at the stability of that solution. The linear stability of solution a equals 0, well, for that we can ignore the cubic term and we can ignore the quadratic term. So it's just given by this term. And so the growth rate of that solution is given by this. So now what do we have? We have mu r is negative. Mu2 has a mu 2r, but that's 0. So actually the real part of this term is always negative. That means the solution a equals 0 is always linearly stable. Let's write that down and then think about what that means. Let's write it as a equals 0. So that's this guy is always linearly stable. When I said always, I meant for all forcing amplitudes. Okay, if it's always linearly stable, that means it can't undergo a bifurcation where that fixed point becomes unstable and another fixed point arises. So in other words, a solution, a nonlinear solution that is actually phase locked to the forcing cannot arise from a bifurcation from this solution. That's kind of weird, but well, that's what we find so far. I mean, of course, it could be there is no nonlinear solution. Okay, well, let's see. But that's what we have so far. This is always linearly stable. There's no branch coming off this. There's no branch of fixed points coming off that solution. No branch of fixed points coming off a infinity 1. Okay, so then we want to have the solution. We are looking for a solution where r is not 0. So we have these two coupled equations, but they have sort of a standard form in the sense that this turns up more often. And so you see that we can couple the phase and the magnitude. If we solve in both equations, in the first equation, we solve for the cosine. Second equation, we solve for the sine. And then we sum up the square of both terms using Pythagoras. And then we get an equation for r alone, because the left-hand side is 0. We're looking for fixed points, right? So when you do that, you get the following equation, which I'm going to just write down. So it's you get like delta squared f squared r squared equals mr minus gamma r squared plus mi minus, I'm just copying that from the notes because but this is just, as I said, just taking the two equations, solving for the trig functions and summing up the squares. So we see this is, what is it? This is a biquadratic equation. It's quartic, but it's biquadratic. Only r squared shows up. And so therefore, when you solve, sort it nicely, so you get r to the 4th times gamma squared minus, and now you get some curly bracket kind of business. Maybe I should write it down once. Again, I'm just copying this. It's because this is sort of just algebra that you don't have to think very hard. You just have to be careful. So that's what you get when you sort for r squared. And so the solution for r squared is given by this curly brace plus minus the square root of that discriminant divided by 2 gamma squared. And so we need to know whether these solutions exist, as in, well, r squared needs to be not only real, it has to be positive, right? So what we need is we need the discriminant here to be positive, and we need to have actually the sum being positive also. So let's look at the discriminant. The discriminant is this curly brace minus m absolute value squared times gamma squared. And so maybe I should write that down. It's easier to see. The discriminant is equal to the curly thing squared minus 4m absolute value squared gamma absolute value squared. And so therefore, because this is positive, the discriminant is always smaller than the square of the curly brace. Or in other words, the square root, if it's real, it's always smaller than the curly brace. So that means both roots here, both values of r squared have the same sign. Whether it's positive or negative is a different question, but it's the same sign. The curly brace needs to be positive, obviously, for having two positive solutions. And then the question is whether this is actually real. So there's one thing that is nice to confirm. We saw in the linear stability of r equals 0 that there's no branch coming off that solution. So that means if we now calculate here the nonlinear solution, this should not have the limiting case that r goes to 0, because that would mean it would match with the other solution and there would be a connecting branch. And indeed, because this is always smaller than the curly brace, this is never 0, right? So that's consistent. That's good. Okay, how to analyze this now? Let's consider large f. The question is whether the r squared ceases to exist as a physical solution, either by the square root becoming imaginary or by the whole thing becoming negative. Now we see for large f going to infinity, we have that the curly brace goes to delta squared f squared, which is positive. Okay, so now as f decreases, so that means the curly brace is positive and we have two roots. Good. Now if f decreases, you could consider that the curly brace could become 0 and then to become negative, and then r squared would disappear in that way. However, as f becomes smaller, as if the curly brace becomes 0, this discriminant becomes negative first, because this minus 4m gamma squared term is negative, right? So before the curly brace becomes 0, the square root becomes imaginary. So the way we lose these solutions is by the discriminant becoming 0. And so this is now still a reasonably complicated expression, to analyze when this thing minus this thing is actually 0. And so let me go for specifically the case we actually have. So we have, in our case, we have gamma r is equal to 0, and mu2r is equal to 0, and the gamma I is negative, as I said before, mu2i is negative. And so if gamma r is 0, then this term disappears. Mu2r is 0. Well, mu2r, what does it show up? It shows up in the mr. But the m is given by It's this abbreviation of mu plus mu2 f squared. And so we have, if you plug that in, we get for our discriminant, we actually get delta to the fourth, f to the fourth, plus 4 delta squared. Oh, I don't need the absolute value squared. You showed that delta has to be positive, or delta can be assumed to be positive. Delta fourth, f to the fourth, plus 4 delta squared, f squared, mi gamma I, minus 4 mr squared, gamma I squared. And so if we now plug in mr back using that mu2r is 0, we get the expression delta fourth plus 4 delta squared mu2I gamma I f to the fourth plus 4 delta squared f squared mu I gamma I minus 4 mu r squared gamma I squared. Okay, so this is a bunch of calculation. I understand it's sort of not very interesting. The point I want to make here is essentially just sort of what kind of, so you have these equations, and even though they're just algebraic equations, you know, to actually extract what's going on takes a little fiddling, and it takes a little fiddling. Let's just leave it at that. And so I want to just illustrate some of that fiddling that we need to do, but we're almost there. And so let's see. We have mu2I is negative, gamma I is negative. This is delta squared. So this number is actually positive. So as f is very large, the discriminant will be positive. So if f going to infinity, delta is positive. When f goes to 0, what do we get then? This is gone. This is gone. We only have this term. So actually then a delta is negative. So delta changes sign as f decreases from large to small values. And so when delta goes to 0, we lose the two solutions. So there is a critical value of f, fc, such that if f is bigger than fc, we have two solutions. And f is smaller than fc, we have no solutions, no solution. And let me just calculate, give the expression for that condition. It's actually nice to write it in terms of, not in terms of f, but rather in terms of, you can also solve the same thing for mu I. And mu I is actually, remember, is the imaginary part of the real of the linear coefficient of A, which tells us the detuning between the forcing and the oscillation, the natural oscillator. And so we can solve for that quantity, and then you get a nice expression which we can easily sort of plot and get a feeling for what's going on. So as the discriminant becomes 0, let's see that clearly. We have both solutions here become the same. So you have the collision of two fixed points. And so you have a saddle node bifurcation. So that's why I want to call it omega Sn. And that then turns out to be delta squared plus 4 mu 2 I gamma I divided by 4 gamma I times f squared minus mu r squared gamma I divided by delta squared 1 over f squared. So again, what's the point of writing this out? Well, the first point is that we can actually make a little phase diagram, which is sort of actually what we're really aiming for. So you can plot the detuning versus the forcing. And let's see, we have mu2I and gamma I are both, let's see, what are the signs of those guys? mu2I, did they go? Mu2i is negative, gamma I is negative, so these are both negative. And gamma I is also negative. So this is negative. So this actually, the first term is a parabola downward. This is diverges as f equals 0. And gamma I is negative, but this is also negative. So it diverges in a positive way. So the curve looks roughly like this. This is the curve of the solenoid bifurcation. Whenever f is larger than that, we have two solutions. And below we have none. Okay, fine. And you can now, if you want, you can sort of make, through that phase diagram, you can do different kind of cuts. You could, for instance, just to have something concrete, you could say, well, for a given detuning, you increase the forcing. And so you would get a bifurcation diagram that looks like that. Increase the forcing for given detuning. And so then there's no solution below a certain value. And at this point, you get a solution. So that's maybe this point. And so then you have a solenoid bifurcation like that. And the solenoid bifurcation occurs here. And so you have these two solutions, and this would be the amplitude R. And this branch does not connect ever with R equals 0. Similarly, you could have a cut in this direction. Maybe let's do it this way. So you make a cut like that. Then at fixed F, you increase omega Sn. And this again, the amplitude. And again, you get a solenoid bifurcation that sort of looks like that. And this would be the bifurcation point. So this raises the following question, and that's why I wanted to go in all these details. Remember when we looked at the subcritical pitchfork bifurcation? Maybe I need to sketch that just to remind you. This makes this a messy figure, but I think we need to just remind ourselves of that situation. So there we had, so there was a subcritical pitchfork. And we had some control parameter, lambda. There was a bifurcation point. And this looks like that, right? And the symmetric part down here. And there we discussed whether it was justified, or under which condition it was justified, to keep the quintic term, which leads to the saturation on this upper branch. And we showed that this is not generically justified. It's only justified if the cubic coefficient, which makes this bifurcation subcritical, if that coefficient is small. Actually, it's only valid, strictly speaking, if we look at the distinguished limit of this cubic coefficient going to 0 and the control parameter going to 0. Then this upper branch shows up at arbitrarily small amplitudes, as it has to if we want supposed to be valid in our Taylor expansion. So that raises the question whether this thing, which is detached from everything as far as you can tell, whether that branch is actually justified. Are we calculating something here that's actually justified, or is it outside the validity of our calculation? And for that, we need to look at the equation for omega Sn, right? So remember, what is small, what is large? So the detuning has to be small. Okay, I should be more clear. All quantities that we write down here are order 1 quantities, but they have been rescaled, right? So the omega Sn is actually the detuning is epsilon squared times omega Sn. Similarly, the forcing is epsilon times F. And similarly, the ur comes from the damping, and ur is epsilon squared times. So okay, so these are, so the mu r is small, F is small, F is small. Well, mu2i is small, and omega Sn is small. And so therefore, you could be very suspecting or suspicious about this 1 over F squared, because we're doing an expansion in small f. So this looks like very large. However, maybe we didn't write that down. We wrote that down earlier, right? So we have, but we see it still in our equation here. The way things are scaled, f is of the same order as a, but mu is of the order of a squared. So mu is of order f squared. And so therefore, the equation that we write down here is actually consistent. We have mu squared divided by f squared. Mu is of order f squared. So this whole thing is actually an order epsilon squared term, as is this guy. Delta is of order 1, and this is not relevant here. So this equation is valid in the limit that f goes to 0, mu goes to 0, and the detuning goes to 0. And so it's really true that in the limit that this is valid, this saddle node bifurcation occurs at arbitrarily small amplitudes near the half bifurcation. And so this bifurcation diagram they've generated is actually a consistent description of what's going on. The only thing we still need to add is that there is also the solution r equals 0, which exists and is linearly stable for all values of f. Okay, so that's sort of an interesting bifurcation diagram because, as I said, this branch does not connect with the other branch, and still it's actually systematically valid in this expansion for small mu and small amplitudes. Okay, so that was a lot of kind of algebra, but the, without the algebra, we wouldn't have been able to actually assess this and get actually an answer for this bifurcation diagram.